I mean, just typo. So the formula for the QQ character contains the integrand contains also the matter polynomials. So there was this G class, which was a product over I, product over A prime. Where xi's were virtual chain roots of the tautological complex, but there is also the contribution of the matter polynomials, which is, I'll just write here. Mu v I, where so this is the chain of the V. So the V spaces, they form a vector bundle over the Nakajima variety. So you can also write the virtual chain roots, which I will denote by nu. So that's the missing term. So they were an example which I presented, but I forgot to put them explicitly. All right. So two more examples of QQ characters. I mean, one I already gave. That was for the one for the quiver with one vertex and one edge. And so that was for the fundamental QQ character. So I will not write it today. So this is just one 0. So this was the sum over the partitions. And the third example is the example for the finite A-type quiver. So this is the quiver with R vertices and the edges of this form. So I will write the formula for the fundamental QQ characters. Here's the formula. So here I will choose the normalization. So this will be my orientation of the edges. And I will choose all bifundamental masses to be equal not to 0, but minus epsilon. As I said, since this is a simply connected graph, you can scale it to any value you want. So now the fundamental L fundamental QQ character, so it's labeled by a choice of a vertex. Here is the formula. Okay, so I will omit. So I will set all matter polynomials to be equal to 1 for simplicity. So you can find the general formulas in my papers. And it's the sum over all subsets of the set 0, 1 up to R of cardinality L. So L goes from 1 to R and I is allowed to contain 0. Then you take a product over all I inside capital I. Okay, so it's a bit complicated, but I want to write it nevertheless so that you will see the analogy to the characters of the. So this should be compared to the characters of the Lth fundamental representation of SL R plus 1. So the lambdas, which I will write, are the analogs of the eigenvalues of the R plus 1 by R plus 1 matrix. So lambda I of x, this is the ratio of y's. I goes from 0 to r, and so my notation is that y0 is equal to 1, and y r plus 1 is equal to 1. This normalization. And now zi's are so zi's are redundant variables, so it's z0 times q1 up to q I minus 1. I. So I from 1 to r. So these z variables are defined up to the overall scale. So there is this 1 over z0 up to zl minus 1. So z0 will actually cancel. And here you put the shift. So the important thing is the shifts, of course. Epsilon hi plus 1 minus l. And finally, hi is a so-called height function. So hi is the it's the number of I prime such that I prime is an I and is strictly less than I. It's so it's a way of ordering the elements of your subset. So you can see it's if not for the shifts, this would be just the linear sum of all combinations of products of eigenvalues in the amount of L out of the set of R plus 1 eigenvalues. So that's like the taking the trace of a matrix in SL R plus 1 in the Lth fundamental representation. But the difference is that there are some shifts here, shifts of the argument. So that's why it's a QQ character, not an ordinary character. And by the way, it actually coincides with the Q character in this case. You see, the only epsilon variable which enters is the sum of epsilon 1 plus epsilon 2. I mean, it algebraically coincides with Kirillov-Reshetykhin QQ character. Okay. So that's it for the examples. Well, okay, so maybe the warning. So the first case where you cannot escape derivatives applied to y functions is the D-type quiver. So okay, so the example number 4, but very sketchy. So if you take D4 quiver, so it's a finite D4. And so these are my vertices. So there are 4 fundamental QQ characters. And so the characters chi1, chi2, chi3, and chi4 have a kind of a simple A-term structure. Again, the D4 corresponds to the group Lie algebra spin 8. And so these outer nodes correspond to the vector and two spin representations, which are 8-dimensional. And the middle node would correspond to the adjoint representation of spin 8, which is 28-dimensional, but the actual formula contains, let's say, 28 simple terms. Plus the term which I will spell out. Plus y2 over of x divided by y2 of x minus epsilon times twice 1 minus epsilon 1 epsilon 2 over epsilon squared plus epsilon 1 or epsilon 2 over epsilon square epsilon, sorry, d by dx. So there's a derivative of logarithm of the ratio. So here you have y1 of x, y3 of x, y4 of x, and the numerator you have y2 of x and y2 of x minus epsilon. And so this is kind of an extra term which you don't see in the classical limit. Classical limit is the limit when either one of epsilons goes to 0. Or some half classical limit, not semi-classical, half classical limit. So then this will disappear, and you get back the trace of the you get the character of the adjoint representation. So that's sort of the adjoint of spin 8. And these are vector S plus and S minus of spin 8. And so what this term represents, it comes from the fact that inside the Nakajima variety of D4 type for the dimensions, so the W vector is 0, 1, 0, 0, and the V vector is 1, 2, 1, 1. So this comes with a Q, so Q1, Q2 squared, Q3, Q4. So that's the weight of this additional term. So inside, there is a P1, which is fixed by the global symmetry, which is so it's non-isolated fixed point. So you cannot make it isolated by any choice of the torus. Yes? Sorry, you cannot make it, you cannot reduce it to points. Yes?
I was just wondering if at any level you technically hold the orientation of your paper, because I don't see any pointer orientation.
I don't. So in defining the quiver variety, I start with the oriented graph. So if you like, let me choose the orientation. Will it make it happier? But the point is that if you change the orientation, you get equivalent formulas, you get isomorphic variety and everything else.
But in type A, for example, you seem to be talking about the fundamental characters, and then they seem to be logician.
So this orientation here was needed when the only place where it was important is when I said that with this orientation, that was my normalization of the bifundamental mass. That was my orientation.
I see that what you said, the orientation is just conventional about group action.
Yeah.
They say you want to scale up the variables by astronomical. That requires choosing the column by orientation. But it doesn't matter if you choose a different orientation with the same action.
Right. It just, I mean, there is a, so this C star, this main C star, which collapses Nakajima varieties to something compact, you can define it by, to act simply by scaling everything with equal weight. But then the weight will be epsilon 1 plus epsilon 2 over 2. And sometimes this 1/2 is inconvenient to deal with. So historically, there was some choice made that if I made the choice of orientation of my quiver, then I would say that I will not scale the B matrices which act along the arrow, and I will only scale the matrices which act against the flow. And in the framing spaces, I will not scale the operators which act from the framing space to the V space, and will scale the operators which act in the opposite way. So that's a choice. But if you don't like the choice, you can redefine your covariant weights and make things uniform. I think if you just think about the example with A1 quiver, when you have one framing space and one fixed space, you can see that. So if you decide to scale both I and j, or if you decide to scale only j, it's equivalent up to a transformation by which you divide anyway, by the V transformation. Okay. So the fact that there is a P1 inside, that's why we have only the first derivative. Okay. All right. Okay, enough of that. So now there's a magic, well, okay. All right, trust me. The origin of species. Well, crossing is part of it, right? Breathing. Okay, so crossed instances. Okay, so let's go back to this ADHM construction we talked about in the first lectures. So remember, so we had the space N and operators I and J, and then we had some matrices B, and then I said that I like to enhance these matrices to add enhance the space of matrices. To include B3 and B4. And then I wrote some equations, and in these equations, there was a hint that there might be some symmetry between B1, B2, and B3, B4. But clearly, B1 and B2 were kind of attached to IJ. And B3 and B4 didn't like I and J, because they were kind of annihilating everything which came from I and J. But this picture is clearly non-symmetric. So let's make it symmetric. So let's introduce another framing space, second framing space, let me call it W, and a new set of operators I tilde and J tilde. And now let's make this whole picture symmetric. So meaning that I will now write equations. So I can introduce left moment map and right moment map. So the left moment map will be the commutator of B1 with B2 plus IJ, and the right moment map will be the commutator of B3 and B4 plus I tilde J tilde. And now we will write equations. So the equations will be that mu C L plus mu C R dagger is equal to 0. And as before, the crossed equations, well, cross commutators, like B1, B3, so 2, 4. and the stability. And the real moment map equation, which will now combine all of these matrices in a happy family. Sorry, this is line kind of low, but it's, so I'm just adding up I mean, I could have written also the real moment maps, mu r. Sorry, mu L. So this is left real moment map, and then the right real moment map. So this last equation is just a sum. I'm just adding up the equations. Mu r left plus mu r right is equal to called zeta, number zeta. There is no point in taking Hermitian conjugate because this is it's a Hermitian matrix, Hermitian operator. And then, so these are all equations which take values in square matrices, and there is an equal number of equations plus symmetries as the number of square matrices. And on top of that, we'll now impose the equations which govern the interaction of B matrices with I matrices and J matrices, and I tilde and J tilde. And this interaction will be limited. Namely, if you want to act with B3, you better not act on it on I. Say it again? Yes. B1 now will not like I tilde. Okay, so now, so these equations, so there are as many equations of the first type as I and J matrices. There are as many equations of the second type as I tilde J tilde matrices. And there are equal number of equations here, and the matrices B1, B2, B3, and B4. So I impose this an equal number of equations and symmetries on my variables. So what I'm getting is something of virtual dimension 0. But I will not stop there. I will actually impose even further equations. And that concerns the interaction of I and J. So what you can do, you can try to go from N to W space by first acting with I and then going using J tilde. So an interesting equation is to forbid that. Namely, J tilde I minus I tilde dagger J dagger is also equal to 0. I mean, okay, so I say the words forbid and doesn't like and so on, but these equations don't seem to be that harsh. However, if you take the squares, open brackets, and simplify things, you will find that these equations actually imply that B3 I is equal to 0, B4 I equals to 0, B1 I tilde is equal to 0, B2 I tilde is equal to 0, and so on. So J B3, so J B3 is equal to 0, J B4 is equal to 0, J tilde B1 is equal to 0, J tilde B2 is equal to 0, J tilde I is equal to 0, J I tilde is equal to 0. So we're trying to cross things, but they cross in a limited fashion. So this is so crossed here stands not for, it stands for cross in a four-dimensional, in a kind of quaternionic sense. So this somehow represents the geometry of a quaternionic cross, so two four-dimensional planes inside in the eight-dimensional space. And we are describing the kind of instantons, so point-like objects which are moving along this cross. So they can move either on one component or another component, or they can cross from one component to another, but they cannot. Once you belong to one of the components, which means that you descend from the image of one of the framing maps, you cannot jump too far into the other component. I'll make it more precise. What I just. Yes. 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 So, well, it's I mean, it's a great question. Unfortunately, the answer is not no. It's there is no obvious differential geometric way of gluing instanton solutions on a singular space. So this is a four-dimensional singular space. So I'm taking two copies of R4 and glue them at one point. You can try to deform it just like curves. So if you have you have a double point on a curve, ZW equals to 0, you can deform it to ZW equals epsilon. So that gives you a smooth curve. So for holomorphic maps, if our problem instead of instantons was the problem of studying holomorphic maps, we know how to deform a holomorphic map from a nodal curve to a map of a smooth curve. With instantons, so first of all, unfortunately, this cross, if you try to describe it by some equation like this, it will not be quaternionic analytic. So you can write it as an equation of this form when Q1 and Q2 are quaternions, and you could deform it to a quaternionic curve of that form, which would again look like something like that. But in general, it is not clear how to smooth out the solutions which the individual components describe, because for one thing is that already the ADHM construction which I'm using does not describe instantons, it describes sheaves. So what? But the other thing which we should keep in mind is that you see these two n spaces and W spaces, so they kind of ranks of the gauge groups on two components, but they don't have to be equal. So it's some crazy object which looks like an UN instanton on one component, UW instanton on another component, some way of smoothing, smoothly, maybe in a non-commutative sense, connecting them, but in such a way that the rank of the gauge group changes. So if n was equal to W, then maybe you could have imagined that some kind of smoothing of that type, which would produce a solution on the deformed space. But But I don't know of, I mean, I'm not aware of such construction at the moment.
No, but it should be like some kind of, some shifting design.
Yes, so you might try, so what I think these equations describe, they describe non-commutative instantons. These instantons should be, they already live, they live in a-dimensional space. You just have, they happen to have a support on a 4-dimensional cross living inside this a-dimensional space. No, it's not that non-commutative. It's non-commutative R8, where the non-commutativity is determined by this parameter zeta, which is simply, well, you just you take you choose a complex, you identify it with a C4, you endow it with a symplectic form. You just do the non-commutative deformation corresponding to that symplectic form. So zeta is so roughly Z A commutator with Z B bar is zeta delta AB. Fortunately, I don't need to know what the space-time interpretation of these matrices is for the construction which I'm doing. So I'm just, it's a tool. For me, it's just a tool, but it's a useful tool. Okay. So dimension? Poisson structure? Degenerate? C4? It could be degenerate, yes. Actually, well, the it's a point?
Around that point.
Ah. Yeah, I don't. Okay, I don't know. So it seems to me that these equations actually correspond to the kind of constant Poisson structure. It need not be non-degenerate. Actually, it's. I think the only thing which is important is that the sum of the commutators. So this sum from 1 to 4. Sorry, from 1 to 4 of commutator ZA with ZA bar is equal to zeta. So it's actually kind of a weak condition. For example, you may have 6, so you may, instead of the R8, you may have a non-commutative R2 times commutative R6. So that will definitely solve this equation. But I really don't know, I don't have the whole construction, so I should not say it. I'm not sure that you can think of something, well, I don't think the. Yes, interpretation of sheaves. It's yeah. It's so so I will explain it now. Okay, so I'll just explain. So that we have, of course, but if you want to have a differential geometric interpretation, that we don't have. So these equations, among other things, they also imply that these moment maps vanish separately, mu c left and mu c right. So they are also which means that for the so you do have ADHM equations except for the stability condition for the quadruple B1, B2, Ij, and for the quadruple B3, B4, I tilde, J tilde. So ADHM data. But they are not completely independent. And so they're not, the only thing which sort of glues them together is the stability condition. So the stability, which is encoded in the real moment map equation, is the following, that the K space is actually the sum of the spaces which are generated by acting with B1, B2 on the image of N, and B3, B4 on the image of W. So now, if you just restrict, so if you choose inside the space K, so there is a subspace. Let's call it K12. So it's what you get by acting. So N takes you from, so I takes you from N to that subspace, and then inside, so you act with B1 and B2, and it doesn't take you outside the subspace. And then similarly, you can define the space K34, and so this is where B3 and B4 act. And so these guys, so that part of the structure defines for you a torsion-free sheaf on P2, let's say P212. So that's a sheaf E with a framing at infinity. So let's call it E12, which is isomorphic to N, and its charge. So its charge is equal to dimension of K12. So there is a torsion-free sheaf. Second Chern class. Torsion-free, rank N. And then that data, so B3, B4, I tilde, J tilde, define. So this is P. So we add to the horizontal line, which is actually a plane. We add the line at infinity and make it a projective space. And so you can also add another line at another infinity. And so that way you get torsion-free sheaf. Torsion-free sheaf E34 over different P2 of rank W and charge K34. But there is another. But these equations describe another. Describe more structure. There is an additional structure which is the intersection of these two spaces, which is possible. So K12 intersected with K34 need not be empty. And what is this space? Well, that's a space which should be annihilated. So they should be annihilated by, inside K12, it should be annihilated by B1 and B2. And inside K34, it should be annihilated by B3 and B4. Because from these equations, it follows that everything. So B3 kills everything in K12, and so does B4. And similarly, B1 kills everything in K34, and so does B2. So if we look at the fixed points, okay, so the global symmetry group, and this is where the variable x will now appear. So the symmetry of my space is the group GLN cross GLW cross C star cube. Well, it's complexified. So actually, the symmetry of the equations is the maximal compact subgroup of this group. And so that group, C star cube, acts on the B matrices by multiplying them by the corresponding by numbers. These numbers should be constrained to multiply to 1. That's why it's a 3-dimensional torus, not a 4-dimensional torus. And then J is multiplied by Q1, Q2, and J tilde is multiplied by Q3, Q4, which is inverse of that. And I tilde I don't touch. So this is as far as this symmetry is concerned. And then GLN, so if H is in GLN and H tilde is in GLW, then there is also H inverse, H here, H tilde inverse. And now you see that the center of that group is, so the center of that group is C star cross C star. So C star N, C star W. The diagonal subgroup of that center acts trivially on my modular space because that's the part which is actually killed by the UK transformations. But the anti-diagonal, so the anti-diagonal subtorus acts non-trivially. And that's the x variable. So x is my, so x is the equivariant parameter for that torus. So the Lie of that is where x belongs. So that's the mystery of the x variable. It's the symmetry which rotates the n and w spaces in opposite directions. When you only look at the ADHM modular space, ADHM construction for n or for w, the center of the corresponding framing group acts trivially on the modular space. But when you cross them together, the anti-diagonal center starts acting non-trivially, and that's the x variable. So that's how we can see it. All right. So now, so crossing actually involves kissing. So let me show you the this is the structure. So this intersection is it's an interesting point, and that's where the these poles and the cancellation occur. So if you look at the fixed locus for the maximal torus of this group, so the maximal torus now of, let me call it T cross. So T cross, but okay, so maybe it's so T cross fixed locus. Well, it's what do we expect? So we have, since we have a maximal torus, let's say we have a maximal torus of GLN and maximal torus of GLW, it means that these spaces split as direct sums of one-dimensional eigenspaces, and out of which eigenspace will grow a piece of k, not a piece of cake, but piece of k, by acting with the I maps, and then acting on them with B1, B2, and B3, B4. As before, if you take the maximal torus, on the fixed locus, the J map, the J will vanish for positive zeta. So J actually is 0, J tilde is 0. And then, so this is the structure of the fixed points, which I will draw in this way. So I'm drawing them actually now in the space. So this is the C, which is the, I think there was a question at the end of Andrei's lecture, which is, where do the equivalent parameters take values? Ah, thank you. So, you see, in Oriental culture, there is this, so the difference between the Occidental and Western and Oriental approaches to science is that in the West, people think that they create things by, inventing theories and proving them. And in the East, people believe that they already exist, and there is some place where they're all kept, and we just, go and grab and get them. So in string theory construction, so these two parts of the cross are parts of the space-time, and so they make up a dimensional part of the space-time, and there is a two-dimensional space left, and that's a space where the covariant parameters live. So it's a copy of C where all the covariant parameters belong. And when we draw a Young diagram, so when we draw it in this, when we try to draw it accurately, so when with some regularity, so this regularity should be actually, so these steps are steps with step epsilon 2 and epsilon 1. So when I drew the formula, that's the content was equal to epsilon 1 times I minus 1 plus epsilon 2 times j minus 1. If epsilon 1 and epsilon 2 were complex numbers, roughly of that magnitude and argument, then the contents would truly just form this lattice-like structure. And in addition, we'll shift them by the value of the equivariant parameter corresponding to the framing. And so these numbers are simply A alpha plus epsilon 1 times I minus 1 plus epsilon 2 times j minus 1 when alpha goes from 1 to n, and I and j belong to the partition lambda alpha. So now these guys were in, so A's were in the Lie algebra of the maximal torus of GLN. And now let me introduce B's, will be in maximal torus. Well, I call them W actually, so let's call it W. Maximal torus of GLW. And now let me draw the contents, which I called sigma box. So sigma box was epsilon 3 times I minus 1 plus epsilon 4 times j minus 1. So now imagine that this is epsilon 3 and this is number epsilon 4. And so these numbers are simply W beta plus sigma square. And so what these numbers are, these are the eigenvalues. So these are all these are eigenvalues of sigma. So this is compensating UK transformation, which was compensating the action of the global symmetry group. And so as long as these eigenvalues are distinct, they give you the direct sum decomposition of the K space. So all this, each blob, each dot here, it's the eigen line in K. So for the maximal torus of my symmetry group, the fixed point set corresponds to various ways of decomposing the K space into the one-dimensional subspaces, which are organized in this structure. So the operators B3 and B4 start somewhere here. They act in this direction. Operators B1 and B2 start here, act in these directions, and they don't talk to each other. So the spaces K1, 2, and K3, 4 simply do not intersect. Now imagine, well, they start growing. And imagine that we now fine-tune our covariant parameters, which means that we, instead of a maximal torus, we choose a subtorus. So we allow for a smaller torus to act on our modular space, so that potentially will enhance the number of fixed points. But now algebraically, since for every fixed point we have this structure, so the only possibility for things to start happening in a non-trivial way is that these pictures start overlapping. And so how can they overlap? Well, they can overlap only when K12 starts overlapping with K34, and they can only allow to overlap over very special subspaces. Namely, on this picture, we need to single out vectors which are killed by both B1 and B2, and so these are these vectors. So this is what killed by B1 and by B2. And similarly, on this picture, we should pay special attention to the vectors which are killed by B3 and B4. Because everything inside, so inside B3 and B4 act non-trivially. They shift you by one position to the left or up. And here B1 and B2 shifted one position to the right or down. So only when you reach the corner is when you're killed. And so only those vectors which are killed by B1, B2 can actually happen to be the same vector as here. And so that's where the kissing occurs. So you move these things, and then they start kissing at some position. So you get the, I call it butterfly picture. So let me rotate things slightly. So this is 1, this is 2, this is 3, and this is 4. So the equivariant parameters. So for this to happen, what has to happen? A sub alpha. So this starts at A sub alpha, and this starts at W sub beta, some values of alpha and beta. And now this vector has the eigenvalue A alpha plus epsilon 1 times I minus 1 plus epsilon 2 times J minus 1. And so for them to coincide, this eigenvalue counted from this side should be equal. So W beta plus epsilon 3 times I minus 1 prime plus epsilon 4 j prime minus 1. And now, because, remember, x corresponding to the anti-diagonal in the center, so you can think of it that all w's carry, they're shifted by x. So it means that x actually, so x is kind of distance between two centers of mass. So you have kind of, well, I mean the way, okay, so the way I think I look at it, so I have my original problem, so I had some number of equivariant parameters, a1, a2, an, and then I had w1, w2, w, sorry for bad choice of parameters, well, maybe I should call them b. And so x is sort of the distance between these two clouds of things. So, well, I'm not sure I follow. Yeah, so this is literally a sub alpha, and this is literally w sub beta, and now this is literally this thing. And here it's, well, it should be maybe plus x. That's what you want? Okay. Yes, that's the position of this. So for this to happen, x has to assume now a special value, which is measured in terms of a alpha, epsilon 1, epsilon 2, epsilon. But what it means now that I decreased the torus by which I act, because I'm now, if you like, I don't allow to act with this antidiagonal torus. It is expressed in terms of the maximal torus of SLN, SLW, and C star cube.
Sorry, I'm having trouble reading the red underneath. Can you just say where the x appears in this equation?
Here's x. So okay, so x is equal to, let me rewrite this equation. So x is w beta minus a alpha plus some integer linear combination of epsilon 1, epsilon 2, and epsilon 3. And there is some, well, these are now integers, because I expressed epsilon 4. So if x has this form, then you make, so then if you were integrating over the space of crossed instantons, and you were integrating by a fixed point formula, then you will see two poles in the formula. One coming from the fixed point of that type, meaning that you've grown a partition out of a sub alpha, which is strictly smaller than what I drew before. So when you removed the corners which were hissing, and the right partition was bigger. And the second pole you will get from a picture when the left guy is bigger and the right guy is smaller. Oh yeah, you're right. Yeah, yes. So sorry, I overdid it. So let me first do one intersection. So, one kiss at a time. So okay. So here, so these 2 points. So these are 2 different points on the multiple crossed instantons. This one and that one. These 2 points are actually kind of 2 points on P1, which describes the kissing process. So the kissing process is the process where this intersection space, K1 intersected with K3, 4, in this case is one-dimensional. And so this P1 parameterizes a linear relation between 2 vectors of the following kind. So the first vector is B1, or maybe I should not use red. So it's B1 to the power I minus 1, B2 to the power j minus 1 applied to I of n alpha. So that's one vector. And then let me multiply it by some number lambda. And then another vector is b3 to the power I prime minus 1, b4 to the power j prime minus 1 applied to I tilde of w beta. And so the kissing means that these vectors are not linearly, they are linearly dependent. So there is a relation of this form. And so lambda mu parameterizes a copy of P1. So that's the fixed P1. That's a fixed locus, which is now non-isolated. And then there are two special cases when one of these vectors actually vanish. In this case, this relation means that either lambda is equal to 0 or mu equals to 0. And these are the cases where the partitions grow. It means that one of the spaces actually misses a vector. And so these are the fixed points which you would normally have. But for these values of equivalent parameters, they will be non-isolated. So in other words, when I say that my torus is smaller, it means that now you see the action on the spaces and the multiplication by q1, q2, q3, q4 is such that this vector and this vector have identical weights. And so if they have equal weights, then potentially they can coincide or can be related. And so this P1 parameterizes all possible ways for them being related. So the important point here is that this is P1. It's a compact space. And more generally, you will get Grassmannians or, yeah, maybe some graded Grass. Well, yes, so it will be some variety of incidence relations of linear subspaces in the vector space. And they are compact.
Localization may not make sense mathematically, I can rewrite it as some integral over.
Yeah, so you see, the space on which we're truly integrating is a perfectly linear space of matrices, B1, B2, B3, B4, I, J, I tilde, J tilde. And on that space, localization makes perfect sense. Yes, yes. Thank you. All right. So this is the beginning of the story of compactness theorem, which says that there are some restrictions on the choice of the subtori. You cannot choose any subtorus. There are subtori for which you do get non-compact fixed loci, but they have nothing to do with the x variable. These are the subtori which you would avoid even for the ADHM modular space. So there is a class of subtori for which the set of fixed points is compact, and that guarantees the absence of poles in the x variable in the integrals which we study. And now the main, yes, and that applies to not only to that modular space which I just described, but also for all orbifold versions of that, so which are just the fixed loci for some discrete subgroups of that group. So in particular, so there was a group of SU2 12 cross U1 cross SU2 34. So it's a symmetry group, which, as the name suggests, so this guy acts linearly on B1, B2, transforms them among themselves, this acts linearly on B3, B4. And this guy scales B1 and B2, J twice as much, and then scales in opposite way B3 and B4, and J tilde in twice as the opposite way. So that's so you can choose a discrete subgroup, finite subgroup of that big group, and you can now define a new modular space, which is the. So you take a fixed locus. Well, okay, so let me do it more slowly. So I choose a discrete finite subgroup of that group, and then I fix its homomorphisms into UN and into UW. So I need that. So once I fix that, then I may, so that defines the action of gamma on that modular space, and now I can take the fixed locus. And now it turns out that you can actually slightly deform this space. Well, slightly, you can deform this in the following way. Namely, the group by which we divide in defining the space of cross instantons okay, how should I say this? Gets broken down to the so these are irreps of gamma. So okay, so this space actually has different components. That's maybe what I should say. So when in the original space, when we fix n, w, and k, so the gamma acts in the way which is prescribed by the homomorphism into the framing spaces and the geometric action. Now that will split into connected. So that splits into some connected components. So these are connected components, m crossed k vector. And so these connected components are labeled by the way the k space splits into irreducible representations of the group. Because the fact that gamma, you deal with gamma fixed locus, it will actually imply that you also induce a certain homomorphism, which may be different for different components of group gamma into UK. So it becomes part of the structure of the connected components. And now you may change the stability conditions. So now when you define the, you will write the real map equations, you can actually change the corresponding levels for different irreps, because you now have the center of the reduced group is much bigger. And so that's what I mean by the deformation. So in this way, what you can get the modular space of quiver instantons, which we discussed already. So that's the case when the group gamma belongs to SU2, 3, 4. You can get the modular space of instantons on asymptotically locally Euclidean spaces. This is when the group gamma acts on SU2, 1, 2 part. You can get the modular space of instantons in the presence of the surface defect. This is when the group gamma belongs to the, let's say, diagonal subgroup of that U1 and the cartan of SU2, 1, 2. So there are many things you can produce by this construction. But the compactness holds in all cases because, it was compact to begin with. Then you slightly deformed it without any topology changes. So that's That's rough argument. So that covers, let me just list it. So instantons in quiver theories. Sorry, what I mean is QQ characters plus instantons in quiver theories. QQ characters plus instantons in quiver theories on the Lie spaces. So these are, remind you, these are resolutions of singularities of the orbifold. So it's one of the AD subgroups of SU2. And in the presence of orbifold, presence of surface defect. For example, you may start with the theory living on a plane and then do the orbifold by the cyclic group action, which rotates only one of the coordinate axes. So the theory on such an orbifold you can view as the ordinary gauge theory in the presence of a surface defect sitting at the locus Z2 equals to 0. So let me distill that general story to an explicit formula for the latter case for the simplest theory with fundamental matter. So A1 theory with fundamental matter. Sorry, what did I do? So remember, for the A1 theory, so it has two parameters n and m, and the only fundamental QQ character had this form. So now what I want to do, I want to add a surface defect. At Z2 equals to 0. So the surface defect, which is obtained by saying that we study instantons on a covering space. Well, so okay, so we want to go from the space with coordinates Z1, Z2 to the space with coordinates Z1, Z2 to some power p. So we call it new good coordinates. And then by allowing various ways for things to transform in going around W equals to 0 under the representations of the cyclic group. So we will need to fix the homomorphism of that group into the color space and into the flavor space. So the surface defect is in particular determined by the choices of these homomorphisms. So these are different types of surface defects. So they break gauge group to the subgroup which commutes with the image of this homomorphism. And in some, well, one example which is interesting is the one, the so-called regular defect. So it's for this defect, P is equal to n, and the n space is a regular representation of the orbifold group. So in decomposing n into reducible representations, each representation occurs once. And now the M space will, I mean, for the good theory is the one where you have two copies of regular representation. y2, well, you can actually already see from here there is something special happening when the number of masses is twice the number of colors. Because you see the y function, it's a rational function for each instanton of degree n. And so the correction term is a rational function of degree. So this function has degree n, and the correction term has degree m minus n. So you would like the correction term to be subdominant, which means that m minus n should not be greater than n. That happens to coincide with a nice condition in gauge theory, which is called asymptotic freedom. And it has to do also with the ability to compute things by expansion in coupling constant. So unfortunately, it actually means that my interpretation, which I start with, namely the kind of four-dimensional quasi-maps, might not be the most interesting in this case. But anyway, so it's nice when m minus n is less than equal or equal to n is kind of critical case. So m equals to n is a kind of a good case. And so if you now, in addition, introduce this orbifold structure, the surface defect, the nice surface defect is when this relation happens for each irreducible representation of the group. So you have, so that's what you have. Okay, so now you can repeat the story of universal sheaves and everything, and the y observable in particular, well, the instantons fractionalize. So that the instantons which in this theory used to have a single parameter, single number k, now will be characterized by n charges, which you can interpret roughly as saying that, so in the presence of a surface defect, so you have a four-dimensional theory. So this is four-dimensional ambient space. And now you have inside it, you have this surface defect. And there's some life which happens on this defect. So this defect, so this R2 is actually being mapped to some space with UN symmetry. It could be just the flag variety, or it's cotangent bundle, or something like that. And so such maps have their own topological charges. And so in addition to the bulk instanton charge, so the number of instantons, which was the number k, you now have additional charges which describe the two-dimensional instantons. So these maps have their own structure. And so k now splits into n numbers, k0, k1, kn minus 1, of which some linear, you can say that some linear combination of them is the bulk charge, and then the rest are the charges describing the maps to the flag variety. Now, accordingly, the y observable, which was some way of capturing the structure of instantons, now also gets fractionalized. So let me explain. So instead of the single observable y of x, we now have n of them, which are labeled by the irreps of the cyclic group. So in our case, it's minus 1. And so what it is, so yx So first of all, it's a product over alpha Okay, so I need to introduce a coloring function. So remember I said that we need to fix the homomorphism from the cyclic group to the color space. So I will describe this homomorphism in the following way, that I will assume that my decomposition of the n space into one-dimensional components, so it commutes with the decomposition into the irreps of Zn. And so the reducible representation corresponding to the color alpha, I'll call C of alpha. So C of alpha take values from 0 to n minus 1. And my assumption is that this is a one-to-one. So it's a one-to-one correspondence. So for each color, there is, sorry, it's the same n, little n. Little n. Little n. Here. Okay, so what am I doing? So I took the formula, so I'm taking the old formula for the y function, which had this product structure, and then there were x minus a alpha c omega c box minus epsilon 2. And out of this formula, I will keep only those terms, only those factors, which have Zn parity equals to omega. So from the first factor, this is what I keep. So if you like, I assign to each letter in this formula a certain Zn representation. So letter x will carry Zn representation 0. A sub alpha carries Zn representation C alpha. Epsilon 1 carries representation 0. Epsilon 2 will carry representation 1. That reflects my the way my orbifold was acting. So Z1, Z2 is multiplied by. So Z2 transforms in the first irreducible representation of my group, discrete group. So epsilon 2 will carry representation 1. And finally, C, so the content of a box carries a representation which is proportional to the number of times epsilon 2 appears in it. So it's j minus 1 when box has coordinates I and j. And so it means that out of this product, so overall, I take a product over all boxes in the representation alpha. So now, different product over all alpha, over all beta, let's say, boxes in representation beta, such that C of beta plus j minus 1 is equal to omega mod n. And so that I keep the first factors, x minus a sub beta minus c delta minus epsilon 1 times the product of all beta, product over all boxes inside the partition lambda beta, such that C of beta plus j is equal to omega mod n. Because here I have an extra addition of epsilon 2, extra addition of epsilon 2. So x minus a sub beta minus c box minus epsilon 1 epsilon minus epsilon 2, sorry. And then x minus a sub beta minus c. That's it. So this is my, so this is the definition of y sub omega. Omega modulo n. It's notation modulo n, because omega is defined modulo n. These are representations of a cyclic group. So j can be very large, but we only care about its residue mod n. So you see what I did, so I took the old formula and then I sort of split it as a product of n factors, each factor having its own, having the specific Zn parity. If I'm not mistaken, the old y observable is still equal to the product of y omega for all omega. So I really fractionalized. In physics language, it's called fractionalization. So now it turns out that the QQ character, so now in a sense, if you like, even to this surface defect, I can assign a kind of a stupid quiver, the quiver for the cyclic group. And so my QQ characters will be now organized according to the fundamental representations of the corresponding Cosmological algebra. So, but you can also do just straightforward now, follow your nose and just do the orbifold projection, just separate components. So from this picture, it follows put it this way, that now the expectation value of the following guy, omega plus 1, x plus epsilon 1, epsilon 2, plus q sub omega. So q sub omega is what couples to one of these charges. So now my instanton charge also gets refined. So my partition function now depends on many more parameters because I have many more topological charges. P sub omega over y sub omega. Has no poles in X. So the same compactness theorem buys you almost for free that powerful statement. But now this is really powerful because unlike the previous guy, y of x, which was a rational function of degree n. And so now if you wanted to use the fact that this guy has no poles, and therefore it is beneficial to expand it for large x and look at the terms, the coefficients at negative degrees of x, and set them to 0, in order to get something meaningful, here you had to expand these products to a very, very high degree, like x to the power minus n minus 1 to get the first negative coefficient. Here, the y omega observable is a rational function of degree 1. So it is enough to expand, to do the expansion like we did earlier today, only to the second order in the exponent. And so the reason why, I got confused earlier was that I was doing the expansion of the regular y function, for which you get lots of cancellations. But when you do the expansion of this function, you get less cancellations, and you get something non-trivial already at x minus 2 order. So what's the time frame now? Let's do the break, and then we'll maybe continue with that and conclude afterwards. Okay. Good.
I'm a little confused.
Yes.
If it's trivial,
If gamma is trivial,
then I just have one theoretical representation, and so I should, and the only kind of y
yes,
territory.
remember this should be periodic. This is 1n.
Yeah.
So gamma is trivial means little n equals to 1.
Yeah.
So it means that this index means nothing.
Right. But then I guess I'm doing the same expansion you were doing earlier in that case.
Right.
So it's not going to be any easier.
Gamma is trivial, nothing is easy. But you see, it's easy only for regular defect. Regular defect means that you choose gamma.
Okay, perfect.
Is the n.
Great.
So you're perfectly right that if my gauge group was U1, if n was equal to 1, then without any defects, we already can calculate this partition function. So these were some applications which I just skipped over. So all integrals over Hilbert scale of points. And we have computed this by this formulas without any defects. That's what by design.
Thanks.
So now I want to re-expand in again in expansion for the following purpose. With the following purpose. So I claim that this expectation So it has no x, and when x goes to infinity with minus, this is actually, it behaves asymptotically, it behaves as x times 1 plus q plus lower degree. So start over. Okay, so it's a function. So this expectation value is a function of x, behaves as a linear function of x when x is large, and has no poles. Therefore, it is a linear function of x. So it is equal to that. And therefore, if we, on the other hand, expand this, so we can write it as 1 plus q omega x plus some operator u omega plus some operator u1 omega x inverse plus delta, then it follows that the expectation value of the operator u1 hat omega is equal to 0 for any omega. And so that's the identity which we want to exploit. And that's why we needed the expansion of y omega, of y function for large x. So let's do this expansion. So now we have this formula. So this is minus epsilon 1 over x minus a minus c. Again, I'm skipping the indices. So this is a restriction on beta and the choice of the box in the Young diagram. Lambda beta. Plus epsilon 1 squared over twice the square of that. I will be only interested in terms up to 1 over x squared in the exponential, because all I want to yes, so I only want to expand this up to x to the minus first power. So with that precision, x minus a minus c squared is equal to x squared. And so this is what the first factor will give me. And then the second factor will give me the plus beta c of beta plus j equal to omega modulo n. Epsilon 1 x minus a minus c minus epsilon 2 plus epsilon 1 squared over twice x squared. And now let's expand it a little bit further. So, so this is equal to minus epsilon 1 over x minus epsilon 1 a plus c divided by x squared. So overall, we can represent this as x minus a c inverse omega times 1 minus, so it's still exponential, sorry, still write this in exponential. So it's minus epsilon 1 k omega over x. So k omega is the charge, which in terms of the Young diagrams is the sum over the the fixed point, the level of fixed points. K sub omega is the sum over all beta, all squares in the Young diagram lambda beta, such that C of beta plus j minus 1 is equal to omega mod n. It's just a number of such squares with the appropriate parity. And let me introduce the notation sigma sub omega. It's the sum of contents. Maybe I should shift it by a. I don't remember. Was it convenient? Let me try that, and then if not, I'll change the notation. So a sub beta plus c, so it's a different sigma from what we used before. C of beta plus j minus 1. Okay, so these are two characteristic numbers which I assign to my set of partitions, and so they show up in the expansion of the y function. So minus epsilon sigma omega over x squared plus, yes? Only u1, yes. Yes, only u1. It will be enough. It will be enough to yeah. K omega twice x squared. We use so we don't need that. So we don't need that. And now from this guy, we'll get plus. So epsilon 1 over x times the number of boxes. You see, now let me write this j minus 1 omega minus 1. So this is k minus 1. And then when I expand this guy, I'll get epsilon 1 sigma omega minus 1 plus epsilon 2 k omega minus 1. So that's an important correction. Divided by x squared plus this guy, epsilon 1 squared k omega minus 1 twice x squared. Okay, so now finally, okay, let me, so this is x minus ac minus omega, and then so we get some number of finite terms, which are simply epsilon 1 k omega minus 1 minus k omega. So that's what I call u0 plus 1 over x. So this is the interesting part. So we get 1 over x, first of all, by taking the square of 1 over x here, we get by expanding the exponent up to 1 over x squared term and multiplying it by x. And so that we get either by taking the square of something, which is epsilon 1 squared over k minus 1 minus k omega squared, or we get by multiplying a times the linear term. So it's minus a c minus 1 omega epsilon 1 k omega minus 1 minus k omega. Or we get by, so we need to expand to the second order. And so that's, and most of it is not important, but one term is important. So that's as usual. So it's epsilon 1 sigma omega minus 1 minus sigma omega plus epsilon 2 k omega minus 1 over, that's it. And then there is this sum term plus epsilon 1, it should be square. plus epsilon 1 squared k omega plus k omega minus 1 over 2. All right, so we've learned an important, so therefore now by doing what I just did, we obtain the following identity, that the expectation value of some function of k's plus epsilon 1 sigma omega minus 1 sigma omega is equal to 0. So everything, so you see, the sigmas, namely these complicated guys, so something which knows about the details of the partition, which appears in this difference form, is related using this identity to the function of k's. Now, function of k's is differential operator second order differential operator in Q's applied to the partition function. Because remember, so K, we have generating parameters for K's, and therefore inserting K in the correlation function is the same thing as just differentiating with respect to Q. So the identity is now is that the differential operator in Q's is equal to the expectation value of the difference sigma omega minus pi minus sigma omega. And now the final step is to take the sum over omega from 0 to n minus 1. Remember that omegas are defined cyclically. So when I take this sum over all omegas, this guy will trivially vanish. And we get a non-trivial differential equation on the partition function. So this differential equation turns out, if you massage this a little bit further, it will turn out to be of the following type. You can isolate. So it is convenient to reparameterize these couplings Q omega in the following way. So the product of all omegas, let me call it Q, this is actually turns out to be the fugacity for the bulk instanton charge. And then the rest of them will parameterize using the variable z in the following fashion. So that Q omega is equal to that when omega is 1 up to n minus 1. So, and Q0 is expressed to Q in this form. So it turns out that this equation will be the first order in Q and second order in Z. Namely, the equation will have the following form: epsilon 1, epsilon 2, Q d by dq acting on Z. So this Z actually, let me call it psi. So you already here you see that there is something that it's beneficial to multiply the partition function by a factor, so let me call it psi, which is to be Z multiplied by a certain factor of the form A sub C inverse, times Z omega. So it's a simple trivial factor, but it simplifies this formula. So you see A shifts K. So K is some kind of an integer part of what will become a momentum, and A is a kind of a continuous part. There is another factor which I will omit. And so for this normalized partition function, the equation has the following form. So this is the second order differential operator in Z by dZ. And then you can show by some change of variables that this equation is precisely the Knižnik-Cosmological equation. So it's Knižnik So it's Knižnik-Cosmological equation for which is obeyed by the conformal block of the current algebra. The current algebra in question being the SLN current algebra. So for SLN current algebra for the 4-point conformal block on a sphere. So it's a 4-point okay, so mu0, mu1 at the point Q, mu2 at the point 1, and mu infinity Q1, mu infinity at infinity. So it's a so this equation is the equation which is obeyed by a 4-point conformal block in WZW theory, or in the, so it's a conformal block of SLN current algebra, which corresponds to a special arrangement of vertex operators. So two of them correspond to the Verma modules of SLN, whose highest weights are determined by the choices of masses m1, m2n, so mn and mn plus 1, m2n. So this enumeration corresponds to the assignment of masses according to the representations of Zn. So that's this way. Remember, I said that I want 2 copies of regular representation. So from which copy one goes into the definition of the vertex operator at the origin, and one goes to the definition of vertex operator at infinity. And the ones in the middle, they correspond to the representations. I forgot what they're called. So they're essentially representations of SLN in functions of n variables. Whose so they are not highest weight representations. They're kind of in the middle, but they have one parameter. So they're representations in functions of the form x1 xn to some complex power lambda. And then you have functions x plus minus. So this way you can make the algebra of SLN act, and you can promote it to the action of Cosmological algebra. And so this one number, lambda, is essentially the center of mass of these m's, and the same for the other vertex operator. Cosmological algebra. No, it's ordinary affine algebra. Affine algebra. Yes. Well, okay. So it was expected that you should get some relation of the the connection between the correlation functions of special observables of 4-dimensional supersymmetric gauge theory to conformal blocks of some 2-dimensional conformal field theory was expected. It was an expectation. There was no clear derivation, so it was not clear how to derive from first principles which conformal theory corresponds to which 4-dimensional gauge theory. And so so the fact that you can actually identify them in simple terms was kind of surprising first, but nowadays people have developed some mnemonic rules, so they can sort of expect more and understand in advance what kind of theory to get from what kind of defect or operator in gauge theory. But I wanted to stress that in some sense, everything I said in these lectures was kind of elementary. You didn't need to know anything in, you know. Okay. So for U2, you can still write this identity, I think, and so in this theory as you know, the Knirig's Cosmological equation in two-dimensional terms is a consequence of the relation between the current algebra and Virasoro algebra. So this is what's hidden here. It's the word identity for Virasoro and Sugawara construction expressing Virasoro through current algebra. So I should say that the level, maybe I should say that the level is epsilon 2 over epsilon 1. So k plus L. Now, if you do it for U2 hat, you still get a closed equation. I think maybe, sorry, in this case, maybe you will not get a closed equation. The problem is that, so the expansion, the deeper expansions of the Q character, they produce the generators of a W algebra, which you can build out of a Celan hat algebra. But until we develop the W geometry, so until we find ways of making our vertex operators in conformal field theory to live not only on the, in complex geometry of the Riemann surfaces, but move them away into the W directions, we don't have, so we cannot write an equation. So you see, the equation which you would like to write would be that now if you promote this correlation function to the function of W parameters, and gauge theory actually does that. So it allows you to introduce higher times. They're precisely analogous to higher times in KP hierarchy and Todek hierarchy. So then the equation which will fall from U2 hat would be that something like a derivative with respect to W3 parameter is equal to the third order differential operator applied to psi. So in a W, this W? You can modify my rules of integration by inserting now on top of everything we've been integrating. You can now integrate the Chern classes of the universal sheaf. I mean, again, restricted to the point, or maybe not restricted to the point, times some parameters. So W3 would be probably corresponding to Chern 3, actually, right? So W2, which is the ordinary complex geometry, which is Q parameter, exponential logarithm of Q, corresponds to Chern 2 in terms of the classes. And that's just K, so that's why it stands outside the integration. But Chern 3 will already be inside the integral. And so that's so in fact, in Kimura and Peston construction, they actually need to use these parameters because that's how they realize the Heisenberg algebra. The Heisenberg algebra for them is well, not surprisingly, is realized as differential operators in these higher times. Now, there is another equation, which another instance of an interesting equation from the world of conformal field theories, namely the beloved Polyakov-Zbolotchkov equation, for which people have derived W analogs. So Sam Biok actually can tell you more about this. And so maybe that's the example with which I should conclude these lectures. So let me just state in words that if you do the similar calculation for the surface defect in the A0 hat theory, you will get the conditional cosmological Bernard equation on the torus. And so then the differential operator on the right-hand side will be the elliptical Legere-Moser Hamiltonian, which is interesting. And then if you take the example of the finite A linear type quiver, okay, sorry, the rule was to do what? Flat. Okay, flat. Okay, so the other example is the following. We take a R-type quiver, and now we take n spaces to be two-dimensional. And then we take m spaces to be two-dimensional at the first node and at the last node. So it means that we have m1 equals 2, mr equals 2, all ni's equals 2, and mi equals to 0 when I is between 2 and r minus 1. So that's an example of the asymptotically conformal theory. So it's a generalization of A1 theory for which you would take 2 and 4. So then this would be kind of collapsed case. And now we'll so in these lectures I discussed the danger of tuning equivariant parameters when by tuning you create poles. But you can also, sometimes it's actually, by tuning you can actually create zeros. Namely, when you choose masses to be in a special way, you can actually truncate your the integration domain to a subspace. Geometrically, what it means is that, again, tuning masses means choosing a smaller flavor group. And when you have a smaller symmetry groups, sometimes you have a choice, you have a larger choice of possible sections for vector bundles whose Euler classes you're computing. And so if your symmetry allows, you may have a section which has sufficiently small, I mean, which is sufficiently non-trivial, so that the set of zeros is sufficiently small. And therefore, your integration problem, if it was original, as our integration problems always involve Euler classes, so we can make our life easier by choosing a section which will just say that we want to integrate over only a very special set of matrices. So in example of the, let's say, ADHM construction, sometimes, for example, you can choose the masses such that B2 applied to I of one of the eigenspaces of n becomes an allowed section. For special masses. And therefore, what it means is that effectively you can set this to 0. And that means that in the set of Young diagrams which will contribute to your partition function, only Young diagrams in which you grow in direction 1 will be allowed, because B2 will have to annihilate everything you make out of the space I of N1. So here we'll do precisely that. So we'll adjust the masses at the first node. So in fact, what I will do, I will say that the first mass is equal to the Coulomb parameter of the first node shifted by epsilon 2. This is exactly what is needed in order to enforce this equation. And I will also say that the second mass is equal to the second Coulomb parameter. So that means that I of n2 is equal to 0. Again, I apologize for my notation. So this is okay. So let me write this. This is first node, first eigenspace, and this is first node, second eigenspace, eigenspace of the color torus. And so this relation means that I'm allowed to write additional equations. So in addition to the whatever IDHM equations I was writing before, I now impose these additional equations. Now, the general choices of masses means that you have vector bundles in which you would have liked to write a section, but you cannot because the masses don't allow you. And so you just have to deal with the Euler class of those vector bundles represented, let's say, using curvature. But here, my masses allow me to write this explicit sections, and so I'm just integrating over smaller space. So now, what happens once we make this choice, again, I will not write this in detail, but what happens is now, since lambda, my partition, lambda 1, has this form, and partition, so lambda 1, 1, and partition lambda 1, 2, is empty because that space is trivial. It means that now we can express the sigma object, which was the sum of the contents. Remember, this is what we get in the expansion of the y function. So now the sum of the contents for this partition is the explicit function of its size. Because this is something which this is something like epsilon 1 times k minus 1 over 2 times a plus k, a times k. And so now, when we expand the ordinary QQ character, so now expanding without any surface defect, expanding all QQ characters for a R quiver, we get closed equations, closed differential equations on the partition function of that theory for the special choice of masses, because now the subleading term, so the 1 over x term, which in the absence of surface defect required the knowledge of the sum of the contents, now is something which we know. It still requires some work, but that's the main idea. And then it turns out that this equation coincides with the BPZ equation, which is obeyed by the correlation functions in the Liouville theory. So this is Liouville conformal field theory. So you study correlation functions of primary operators in Virasoro algebra. The number of these operators for the quiver of size r will be r plus 3. So let me first take to be 0. And so it will be r plus 2. So in general, so the conformal blocks for the Virasoro algebra, they are just some special functions. They don't obey any equations. But if the dimension of the primary field has a special value which corresponds to the appearance of a null vector in the Verma module built on top of the highest weight vector, then you get a non-trivial relation, differential relation, following from the conformal Born identities. So for delta 0 equals minus a half minus 3/4 b squared, or b minus 2, where b is determined through the central charge. So this is this is B, 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 B. Okay. So this is Virasoro central charge C, and delta is the highest weight. So once this condition is obeyed, you get a relation. Relation is, so that was derived by Belavin, Polyakov, and Cosmological. Well, namely, the relation is that 3 divided by twice. So I'm writing this in a complicated way because I don't know in advance whether it will be b squared or b inverse squared. D by dz not squared plus sum I not equal to 0, delta I. If I call this psi. And then, in addition to that equation, there are also standard global SL2 invariance conditions. So there are 3 conditions, namely the sum d by dzi dz0 psi equals to 0. So you have 4 equations on the function of r plus 3 variables. And these equations are first order. So they allow you to, in a sense, you can set z0 to be 0, zr plus 2 to be infinity, zr plus 1 to be 1. And then in this normalization, zi will be identified with qi, with the parameters of gauge theory. So then we have exactly r parameters. And we'll get exactly one, effectively, second-order differential equation, which will coincide with the equation we'll get from the QQ characters for the linear curve theory. And further, by taking various limits, so this coefficient will turn out to be essentially epsilon 2 over epsilon 1. And everywhere else, there will be epsilon 1 appearing. And so if you take a limit when epsilon 2 goes to 0, when epsilon 1 goes to 0, in one of these 2 limits, from this equation, you can get the Penn-Levé equation, Penn-Levé 6 for the, in the simplest case of r equals to 1. And so then you can, you get some interesting connection to the theory of isomonodromic equations. In another limit, you'll get a second-order Fuchsian equation, and you get a relation between the uniformization theory, the theory of constant curvature metrics, classical Liouville theory, study of operas, and so on and so forth. So all this is contained in more or less explicit form in the studies of gauge theory correlation functions, which I encourage you to study. Thank you very much. Yes?
You mentioned several times that you integrate mostly Euler classes or something. Yes. Apology that sometimes L classes like responsible not for Euler characteristic but for signature. Is there any meaning if this, because there are some other nice classes that might be useful.
Okay, so first of all, what I call order class, once I go to K-theory, I think will be called kind of what class. But I don't, so I'm not sure, so I think signatures are kind of bad class to get out of this. Does it show up as a limit? Maybe
Because for the expression for this localization formula would be very close to
just a question whether see, the one
because signature almost has other characteristic, has addition properties. If you put two pieces together, you add this.
right. So what I mean by the order class, so for whatever bundles or sheaves I have, usually the object which shows up eventually in K-theory or in Chenkar form is some alternates, is some sum of the following type. When you have some parameter which will be called y minus y. And so this E could be tangent space or could be one with subtraction shifts. I just don't remember whether by specifying y, you can, maybe in a limited case, by specifying y, you can get a signature. I don't remember.
This gives you like question.
Say again, I'm just asking why not to try.
Well, see, the question is whether, so after all these order classes, they themselves were the results of localization. So if there is the success here was that they were found two geometric objects, one which you can project to another. And then you start with something trivial on top, and then project, that generates all these order classes of the tangent spaces of the fibers, or normal spaces. If you can interpret the signature in the, well, the signature is in some sense it's also index of Dirac operator coupled to this.
So the index of some operator.
What is just index of Dirac operator P?
Dirac. It's like Dirac gives you AG, A class.
Yeah, it's expanded. So in 4 dimensions, for example, a root genus is signature.
Can I ask you two kind of big picture questions? One is that we have the totality of all possible observables in some gauge theory, and you write some equations on it. Is that the sense that this determines them all, or determines them all up to some uncertainty we still don't know? Is it
So if I, well, first of all, I do not write equations on the totality of observables.
No, but effectively you have, right? You can put all possible kind of topological classes inside.
Well,
And then
the equations become, I don't really know how to solve these equations except in the case of rank 1, where things are expected to be simple. So you see, what happens is now, what Andre is asking is that if we do add higher times to the problem, which would make this partition function look more like a tau function. Now we introduce, in addition to views, we'll now introduce additional times, that we call TK, which is roughly saying that in the sum of the partitions, for example, whatever weight of the partitions I had before, I will now multiply by infinite exponential of infinite sum TK, then roughly speaking, the sum of the contents to the power k. This is very rough. So now if you have a function of all possible variables, there are equations that are the base, but
No, you have somehow countably many numbers, you have countably many equations.
yeah. So well, let's see. So see, the equation I'm not saying it's not possible, but I haven't developed tools to do this. In some sense, Igor actually has those tools, but it's a different project. So the first, the simplest character, cubic character which we discussed, will be now modified to the following character. We now have this formal power series in exponent. And you claim and say that this function is an entire function of x. So it's kind of difficult to deal with it because if you really try, at least the way I did it before. So explaining at infinity it's not a good thing to do because like an essential singularity and exponential.
No, but you differentiate. It's like the analogy here would be like this, like Virasor constraints in Grove latency. Very, very generally, for a large class of manifolds, this are known, the constraint is unique. So then you can ask them, or if it's not unique, it may be up to something we don't know.
Well, my feeling always was that that modification of the theory, this is like analogous to doing stationary circle Grove latency. So this is,
Yes.
see, Virasor constraints, they allow you to reparameterize the complex plane which I had on this blackboard, which kept all the covariant parameters of all problems. And so, since it was a plane, the line of the covariant parameters, it had some preferred parameterization. Namely, if you take exponential of the algebra, you should land in legal. So that sort of embeds a lattice into this space. But if you decide to break this, so do arbitrary parameterizations, then you get Virasor constraints which tell you that you can reparameterize it back. That's the way it works with theory. So I think in some sense these equations, the fact that this has no
but you
poles,
don't treat it like this. You take some finely many derivatives and
yes.
say
Well, you expand, you use formal power series in T.
Yeah.
Well,
Okay.
I don't know how to
Okay,
solve
okay.
it, how to use it efficiently, but maybe someday somebody.
Was it
Yeah,
say
there-
rank 1? You mentioned that it.
In rank 1, I can solve this equation. Yes, so the fact that this equation, this function has no poles, at least so in the limit shade case, when one of the epsilons is set to 0, sorry, if this is 0, I can solve this.
No, but also this corresponds to the fact that if you take the Hilbert scheme of points in the plane, there would be like some kind of analog Virasor constraints there, which are known to constrain unique. So that's somehow.
Constrain what about it uniquely?
I mean, just compute all possible expectations
Of what bundles?
of all one.
All tautological bundles?
Yeah, tautological, yeah. And so then the other.
What I'm trying to say that.
So another big question. Hold on.
For epsilon 1 equal minus epsilon 2.
But if it's constrains them for a special point, or constrains them for
I don't recall whether these are Virasor
because
constraints.
your equations are true for generic points.
Yeah.
And so therefore, if they constrain them for a special point, they constrain them for generic points. So that's second big question. Big picture question. No, question small, picture. So do you have a way to think about not just some function in one theory equals some other function in the other theory, but you can you match like pieces? Like some pieces you use here actually match some pieces you use there, or is the level of final answer things
Well, it's a good question. I don't know. Well, if you just take these examples which I just reviewed, that the resummed instant-on partition function in four-dimensional gauge theory is equal to the conformal block of some two-dimensional conformal field theory.
Exactly. So you would like
So
to.
now the piece of the instant-on partition function with, let's say, some contribution of specific instant-on charge. Or maybe not just what
No, you'd like to say, you have a vertex operator with an operator from space to another. You'd like to interpret that in gauge theory, and then interpret the correlation function in gauge theory, and stuff like that. Take that
well,
formula
had some
apart.
success.
Right, but in some world which your theory now covers, in some bigger, somehow larger world, you know how to do this.
Well, my feeling, I think, unfortunately, to really see interesting vertex operators, let's say two-dimensional theory, you need to go beyond the standard setup of four-dimensional gauge theory. You need to study something, domain walls, separate different kinds of theories. And, even though this seems to be quite interesting and possible, it's not.
It's like maybe you effectively had some kind of four-dimensional setup. Can you have that get more?
Four complex dimensional setup?
Right, for a complex dimensional setup. Can you add more, whatever, some kind of more defects there to see all the vertex?
Well, one thing which I didn't cover the folded and spiked instant concept, which is when you start, inserting things in all possible directions, and then you can start also filling things up, so you can then really go up all the way into the four dimensions. I don't think we counterpart of that in any two-dimensional context. I don't know if it exists. I only patented the name for the whatever algebraic structure which will come out. I will call it Mama algebra. So it will cover the representation theory of all toroidal algebras for all ranks.
Can I ask a tiny question? This morning you wrote down a formula for QQ character associated to an arbitrary quiver.
Yes.
But we only saw instant cross instantons for the 1 point
Yes,
quiver.
but okay, so maybe I didn't say it loudly enough. So remember, I had this discussion of gamma fixed locus. So that's how you get the formula for the arbitrary quiver. You choose gamma to be an AT subgroup of SU234, and from that you will get the formula which
Arbitrary ATE quiver.
That's ATE, right?
Arbitrary like ATE quiver.
arbitrary AT.
But
But gammas which were allowed by this construction are more than just AT quivers. Of course, they are less than arbitrary gamma quivers, but more than just the usual AT quivers. But at least the formula which I wrote earlier as an integral of the Kachelov variety is a direct consequence. It's just the application of that for gamma, which is the Mackay, which is the AT.
in general, you expect this whole cancellation to be arbitrary.
Yes, yes. So in my papers, I have a proof of, I write a proof of compactness theorem for an arbitrary quiver. So I define the cross instantons for arbitrary quivers. In the practical application of that, to my mind, are kind of limited because typically you will get these sums will be infinite, so these varieties for arbitrary quivers will leave some wild sums, and most likely these will be formal series, formal power series will not be very.